Hello, Luke. Welcome to lesson 66. Today we're going to be talking about two things, really. The simplification of radical expressions and square roots of larger numbers. But these two topics, they're both very related. They're both dealing with square roots. So really today we're just continuing our study of square roots and how we can manipulate them and simplify them. So let's get started. Let's look at the square root of 50. And we're just going to take this as a practice problem, just a little bit of a review on what we've learned so far regarding square roots. So if I take the square root of 50 and I tell you to simplify this, okay, recall the steps that we used to do that. The first step was to take the number under the radical sign, the 50, the radicand, and we're going to find its prime factors. So if we find the prime factors, we're going to have 2, 25, and then we have a 5, and then we have a 5, right? So we can write the square root of 50 as the square root of 2 times 5 times 5, right? Which then can also be, if I just move this out of the way, give us a little more room, can also be written as the square root of 2 times the square root of 5 times the square root of 5. Remember the properties of roots. We can do this. We can take, the product of the numbers inside the radical, the radicand, and separate them into separate roots. So this becomes the square root of 2 times the square root of 5 times the square root of 5. All right? It's one of the properties of any root. Okay, so now taking that, we know that the square root of 5 times the square root of 5 is going to be 5, right? Because any square root times itself is always going to be just the radicand, what's underneath the square root, right? So using that property, we can say square root of 5 times square root of 5 is a 5, and then we have a square root of 2 left over. Okay, so that is the simplified version of this square root of 50. They represent the same value. We haven't changed the value at all, but we have changed the appearance. And we've simplified the square root. We've made the root part of this expression smaller. Okay? All right, so now let's apply that to larger expressions. Same process, but just larger expressions. So if I have the square root of 18 and I'm adding that to the square root of 8, obviously I can't add these like we did in a previous lesson where we had things like the square root of 3 plus 4 times the square root of 3. Remember, we kind of treated the root as a variable, and we said, oh, well, this has the same root. It's both the square root of 3, so I can add the coefficients. So the square root of 3 plus 4 times the square root of 3 is going to be equal to 5 times the square root of 3, right? Hopefully you remember doing that. Just combining these square roots when they're the same. Here they are not the same, so I cannot kind of combine the coefficients of these roots. So there's not much I can do, but or at least up to this point, we haven't learned that there's much that we can do. But let's try to simplify them. We do know how to do that. So can't add, but let's simplify. So let's take that first one, the square root of 18, and we'll just find the prime factors for 18, which are going to be 3, 6. I guess I could have started with a 2, 3. So we have a 2, 3, 3. Okay? So we have the square root of 18 times the square... Oh, what am I doing? The square root of 2 times 3 times 3. There we go. Just the prime factors, right? And then we're adding that to the square root of 8, but 8, if I break that down, is going to be 3 2's. So it's going to be square root of 2 times 2 times 2, right? And now I can separate these factors into their own roots. So I end up with, square root of 2, and I'm kind of making more steps here than I need to. Some of this we could probably do in our heads, but just to make sure that you understand where we're getting all this, we have the square root of 2 times the square root of 3 times the square root of 3, And then we're adding that to the square root of 2 times the square root of 2 times the square root of 2. Okay, right? Next step is we look for pairs because this is a squared root. Remember, if this was a cubed root, we'd look for triplets and so forth. But because it's a squared root, we're looking for pairs. So in the first term here, we have 2 3s. Maybe I'll change my color here. We have 2 3s. So square root of 3 times the square root of 3, that's going to give me 3, right? And then we still have this square root of 2 left over. Then we have this plus, and then over here we have a pair of square root of 2's. That's going to give us 2. We still have one more square root of 2 left over. And now, if we look at it, because we simplified it, lo and behold, we ended up with an expression that we can actually add. Because they do now have the exact same root. They're both the square root of 2, right? Just like what we had up here. We had square root of 3's. They were similar, so we were able to add the coefficients. Now, these are similar. Yay! So we can add the coefficients. The coefficients will add up to be 5, right? 2 plus 3. And then, of course, we still have the square root of 2. Remember, we treat it kind of like a variable. It doesn't change. It just stays square root of 2. All right, so there we go. In the end, we were able to add this expression, but we first had to simplify it. Okay, so we couldn't add here. We simplified. Lo and behold, we were able to add, and we got this. Now, this is obviously kind of a contrived problem. Not always would you end up with like roots, but they're just showing you that that's a possibility. So it's always good to simplify your roots to find out whether or not you could add them. Okay? All right, let's try another one here. So we have the square root of 27 minus 3 times the square root of 18 minus 6 times the square root of 5. So again, the first step, well, actually, you know what? Pause the video. Go ahead and try this one on your own, and then we'll do it together. All right, so let's take the first one. The first step is to break it down into its prime factors. So we have a 27, and if we break that down, we end up with a 3 and a 3 and a 3. Okay, and I'm just going to do all of them here. We also have an 18. An 18 is going to be a 2, a 3, and a 3, just like last time. And then a 45 is going to be a 3, which is going to be a 15, which will be a 3 again, and a 5. Okay, so there, I've kind of broken them all down. Now let's take this first one, this square root of 27, and look at its prime factors and look for pairs. So we have a pair here. So they will kind of equate to a 3, okay? Because this is, you know, I'm kind of jumping, I'm kind of skipping a few steps. I'm doing them in my head. I'm just collecting those pairs because this, well, maybe this first one I'll write it all out so that you can see. So this first one would be the square root of 3 times 3 times 3. But then that could be written as square root of 3 times square root of 3 times square root of 3. And this pair of 3's here can combine to give us a 3. So we end up with the square root of 3 times the square root of 3 left over. Okay, I was just doing some of that in my head. I was just saying, okay, we have 2 3's, so they will equate to this 3 here. And then I have 1 3 left over. That's the leftover square root of 3. So I was maybe doing a little bit more in my head than I should have, but once you get comfortable with these, you'll be able to do that. Okay? All right, so that's the first term. So now we have 3 times the square root of 3. Now let's look at the next term, which is a 3, obviously. That's not going to change. This 3 here, that's just going to come straight down. We get our 3. Now we have the square root of 18. And the square root of 18, we have already broken that down. So the square root of 18 is going to be the square root of 2 times the square root of 3 times the square root of 3. We can combine these 2 3's to give us a 3. And then, of course, we have the leftover square root of 2. So this is going to become the first 3 that was already there multiplied by this 3 that we pulled out of the root, and then multiplied again by what's left over, which is the square root of 2. So make sure you understand how I got this. This one's a little bit different because it has a coefficient out here. The other ones that we've done so far have not. So watch out, because this new number that we pull out of the root when we reduce it has to be multiplied by whatever's out here. And up to this point, it's been a 1 because it's been the invisible 1. But here we have a 3. So we have to multiply it by that 3. All right? So make sure you see how I got from here to here. All right. Then let's move on. The next one we have minus 6 is the coefficient, which we're just going to bring that straight down. And then we have the 335, which again is going to be a square root of 3 times the square root of 3 times the square root of 5. These can combine to give us a 3, and then we have what's left over, the square root of 5. So we end up with minus 6 times, again, notice the multiplication here, 3 times the square root of 5. Okay? All right, so hopefully you see how we got from each one of these terms to the reduced term. Now we can go ahead and multiply these out, kind of simplify them a little bit more. We end up with 3 times the square root of 3. There's nothing we can do there. Minus 9 times the square root of 2 minus 18 times the square root of 5. All right, so very good. So that would be our solution. And notice in this case, by reducing these or simplifying these radicals, we weren't able to come up with anything that could be added. We have the square root of 3, square root of 2, square root of 5. They're all different. So we weren't able to combine any of these terms. However, we were able to make these radicals smaller, which is always a good thing. All right, very good. So let's try one more here before we move on. And this next one is going to be, let's see, how about 8 times the square root of 27? And by the way, I'm just basically pulling these problems straight out from your book. All right, so let's try this one. Go ahead and pause the video and try to simplify and, if you can, combine these expressions. All right, so let's see how you did. We have our two expressions, our two terms, and we'll take the square root of 27. Let's take that 27 and break it down into its prime factors, which are going to be 3, 3, and 3, just like last time, I believe. And now we have 75. 75, a little bit of a bigger number. That can be broken down into 3, can go into it 25 times, and 5, and 5. All right, so there we go. We have our prime factors. Now let's start simplifying here. So we have this 8. It's just going to be brought right down. Nothing changes there. We have the square root of 27, which could be written as the square root of 3 times the square root of 3 times the square root of 3. We can combine these two 3's into a single 3 without the radical. And then we have what's left over, the square root of 3. So this is what we'd end up with. So we multiply this by 3 times the square root of 3, minus, bring this 3 down again. Now I have the square root of 75, and of course that is going to be a square root of 3 times the square root of 5 times the square root of 5. These two 5's can combine into a single 5 without the radical. And then we have what's left over. So we have 5 times the square root of 3. So we have over here times 5 times the square root of 3. Now we can multiply things out here in these kind of these coefficients. So 8 times 3 is 24, square root of 3, minus 3 times 5 is 15, square root of 3. And then finally, let's look to see if we can combine these expressions, or these terms. And in this case, we can, right? Because they both have the same root. They both have the square root of 3. So we can combine these. 24 minus 15 is going to be a 9. And then the square root of 3 is obviously just going to remain. So we have 9 times the square root of 3 as our final answer. All right? Excellent. Hopefully that makes sense to you. Now, let's move on, and we're going to talk about square roots of large numbers. Okay? And to begin with this, let's just talk about this one here. So we have the square root of 75, which, yeah, we just did one with a square root of 75, but that's all right. So we have the square root of 75, and let's say I'm trying to simplify it. Now, we could do what we just did previously over here, which is where we took the square root of 75 and we broke the 75 down into its prime factors and then, found pairs and what's left over. We could certainly do that here again. But sometimes it's good to recognize other ways to do things. And what you might be able to recognize in this particular number is that 75 could be written as 25 times 3, right? Think of quarters. 75 is 3 quarters. 25 times 3. All right? So this could be written as the square root of 25 times 3. Now, that could be written again as square root of 25 times the square root of 3. And the square root of 25 is a perfect square, meaning there is a simple solution to square root of 25. The square root of 25 is 5, right? Because 5 times 5 is 25. So right away, we should be able to look at this and go, oh, that's an easy root. You know, I can take that one and just do that one in my head. So the square root of 25, I know that's a 5. That's easy. And I end up with the remaining square root of 3. So 5 times the square root of 3. Okay, which notice that's exactly what we got over here when we did it the other way. So it doesn't make any difference. The only thing is here, we're kind of taking a little bit of a shortcut and recognizing that this could be written as a product in which one of the factors is a perfect square and easy to find the square root for. Okay? So that's kind of the principle that we're going to use on some other numbers as well. So for example, the square root of 63. Now I could take that and break it down into its prime factors. It'd be a perfectly legitimate way of doing this. But another thing to recognize maybe is that 63 can be written as 9 times 7, right? 9 times 7 is 63. And so I could put that under the square root and then recognize that the square root of 9 is easy, right? Because this is the square root of 9 times the square root of 7. So the square root of 9 is easy. What's the square root of 9? It's 3, right? So we end up with 3 times what's left over, the square root of 7. So 3 times the square root of 7 would be our solution. Okay? So again, we could have, taken that 63 and broke it down into all of its factors and then combine the two 3's into a 3 and then have the leftover 7 and gotten the same thing. Whichever way is easiest for you, feel free to do. Okay? But that being said, we will use this idea to solve much larger numbers. Okay? So first off, though, let's just do a quick review on 10 raised to a power. Okay, so if I have the number 10 and I raise it to a power, or another way to think of that is just I take 10 and I multiply it by itself. Okay, remember the products for these are always really easy because all we have to do is just add up the zeros. All right, we're going to have a 1 followed by the total number of zeros that we see in the problem. So we have a 0 here, we have a 0 here, so we're going to put 2 zeros, and 10 times 10 is 100. 10 squared is 100. So you can think of 10 squared as being a number 1 with 2 zeros. Okay, so 10 to the 4th, for example. Well, that's just going to be a 1 with 4 zeros. 1, 2, 3, 4. It's 10,000. Okay, 10 to the 8th. Well, that's just going to be a 1 with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 100 million. All right, that's kind of the quick way of multiplying these numbers out. Now we can apply that also to hundreds as well. So if I take a 100 and I raise it to the second power, what that means is that I'm going to take the number of zeros and I'm going to multiply it by 2. Okay, because what this really means is 100 times 100. Okay, and you're just going to either, add these zeros up. We have 4 zeros total, so it's going to be a 1 followed by 4 zeros, which would be 10,000. Or if you want to just go back to the exponent, version of this, 100 raised to the second power, we're just taking those zeros and we're doubling them. All right, just think of doubling those zeros. Here was also really what we were doing here. You might argue that's exactly what we were doing here as well. So a 0, we were just doubling the number. There's one of them right here. We double it, and we end up with 2. There's there's one of them right here. We quadruple it. We don't double it this time. We quadruple it, and 1 times 4 is 4, so we have 4 zeros. Okay? So here it's kind of the same thing, only we're starting with 2 zeros. So we have 2 zeros, and then we're going to double those, and we end up with 4 zeros. If I have 100 raised to the 4th power, I'm going to start with 2 zeros, and then I'm quadrupling them. So 2 times 4 is going to be 8 zeros. So I have a 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So kind of extending that, we could look at 1,000. So if we look at 1,000 raised to the 2nd power, this is going to be a 1 with how many zeros after it? What do you think? Well, if you said 6, you were right, because we have 3 zeros here. We're doubling them, so 3 doubled is 6. So we end up with 1, 2, 3, 4, 5, 6 zeros. Okay? If we have, 10,000 squared, again, we have 4 zeros. We're going to double it. That's going to give us 8 zeros. So we end up with 1 and a following of 1, 2, 3, 4, 5, 6, 7, 8 zeros. There we go. All right, so that's just kind of a quick review on how this all works. But now we're going to use that to solve some pretty large root problems, or I should say to simplify some pretty large root problems. So let's take a problem. Let's say I've got, let's say that I've got the square root of 1,000. Yeah, let's go 10,000. All right. So what would be the answer to this? Well, it's pretty simple, actually. So we're going to be doing the opposite of what we did up here. Okay. I don't know if we had a 10,000 up here. Yeah, it was this one right here. So we're saying if I have 10,000 and I square root it, what number multiplied by itself would give me this? Well, here we already found actually that number is going to be 100, because 100 times 100 is going to equal 10,000. So we know the answer is going to be 100. But how could we arrive at that answer a little bit more quickly? And the trick is looking at the number of zeros. So if I have, in this case, 4 zeros, okay, and I'm square rooting it, all we need to do is cut the number of zeros in half, because this is a square root. If it were a third root, then we'd have to cut it into 3 parts. In fourth root, we'd have to cut it into 4 parts, and so forth. But here, we're square rooting it, so we're only going to cut it in half. So we have 4 zeros. We're going to eliminate 2 of them, because that would be half of them. And what are we left over with? We're left over with 100. That is our solution. Okay? So do you see how easy that was? All we're doing is counting up the number of zeros, cutting those numbers in half, or that number in half, and then placing that many zeros after a 1. All right, so if I have the square root of, let's say 1,000,000, okay, what would be the solution to this? Or, yeah, well, in this case, what would be the solution to the square root of 1,000,000? All right, well, let's take a look at it. So we have 6 zeros in this case. Because this is squared, we're going to cut them in half. So we lose 3 of them. And what are we left with? We're left with 3 zeros. So we're going to have a 1 followed by 3 zeros. The answer is 1,000. Okay? It's that simple. Now, how could we apply this to maybe some trickier problems? So what happens if I have the square root of 50,000? Okay, square root of 50,000. Well, the trick here is trying to break this up into something with a 1 in it, a 1 with a bunch of zeros. So I'm going to rewrite this as the square root of 10,000 times 5. All right, do you see how that works? 10,000 times 5 is clearly 50,000, so I haven't changed the value. But what I have done is I've broken it up so that one of the factors is a 1 followed by an even number of zeros. Okay, in this case, 4 zeros. So this could be written then as the square root of 10,000 times the square root of 5. Okay, square root of 10,000 has 4 zeros, so we just lose 2 of those zeros, and we end up with 100, so it's 100 times the square root of 5. All right? See how that works? Hopefully it makes sense to you. Let's try another one now. How about this one? This one will be even a little trickier. What happens if we get something that looks like... Actually, let's try this one. This is a good one. 6,000. All right. Now the trick here is that well, first of all, let's just do the steps we've already learned. So we're trying to get this into, a set of factors where it's one of them is a 1 followed by zeros. So we could say that this is equivalent to 1,000 times 6, right? Now here we have a problem though. And the problem is, if I take the square root of 1,000, can we apply what we've learned to the square root of 1,000? You might say, well, okay, let's look at the number of zeros. We have 3 zeros. Let's cut them in half. But I can't, right? I can't cut 3 zeros in half. It's not an even number. If I were to cut it in half, I'd have to cut 1 full zero, and then I have to cut like a half a zero, which doesn't make any mathematical sense, right? So I can't actually... separate or divide these 3 zeros evenly in 2 ways. So what do I have to do? If we have an odd number of zeros, are we stuck? Well, the answer is no, we're not stuck. But we have to manipulate this problem a little bit more so that we have an even number of zeros. Okay? So what I'm going to do is I'm going to say that this is equal to, and instead of taking the odd number of zeros here, which is 3 of them, I'm going to take the closest even number, which would be 2, right? That's the most I could pull out that would be an even number. So I'm going to pull out 2 zeros, all right, and keep the 1 with that. So I'm going to pull out a 100, right? A 100. This 100, so that I have the even zeros. But I can't change the value, so I have to multiply this 100 by something. I have to multiply it by a 10, right? Because if I take 100 and multiply it by a 10, I simply add a 0 to 100, and that gives me this 1,000. So I'm just kind of breaking this 1,000 down so that it'll have an even number of zeros on one factor, but I don't change the value. So 100 times 10. Now don't forget, I have this times 6 here as well, so he has to stay. Okay? Now I've got 3 factors in here, but one of them is a really easy perfect square, the 100. So I would write this as the square root of 100 times the square root of 10. Well, actually, let's just combine that times the square root of 60. 10 times 6 is 60. Okay? And the square root of 100, well, that's simple now because now I have an even number of zeros. So I just get rid of half of them and see what's left over. I have a 10. And then that's going to be multiplied by the square root of 60. Okay, now we're still not done really in this problem because we could then, factor out 60 and simplify 60 even more. So if we take 60, and we find the prime factors for it, we have 2, 30, 2, 15, 3, and 5, and we note that we have a pair of 2's. So then we can pull that 2 out, set it next to the 10, times what's left over, a 3 and a 5, which is going to be a 15. So we end up with 20 times the square root of 15. Okay? So still a little bit of work, but knowing these tricks did actually help us because we were way up at 6,000. And trying to take, the prime factorization of 6,000, that's going to be a bit of a pain, right? So it did actually help quite a bit that we were first able to separate this into a factor of 0, a 1 with zeros and another number, and then take that 1 with the zeros and force it into a 1 with an even number of zeros so that we could then find the simple square root of that number. All right? So hopefully you understand how that went down. Let's try another one here on your own and see how you do. Remember, the key is you're trying to get even numbers of zeros. That's the key. Even numbers of zeros. So let's try this one. Let's do the square root of 500,000. So why don't you pause the video, give this one a whirl, and see how you do. All right, so again, we're going to try to break this down, and I might start by breaking it down into a 5 times 100,000, right? 5 times 100,000 is going to be 500,000, but that needs to be broken down further because this has an odd number of zeros. So we're going to break it down into a 5 times, now again, I'm going to look at what's the most number of evens, the highest even number of zeros that I can pull out here. And that was going to be 4, right? I just need to lose 1 0. So we're going to take those 4 zeros, which would be 1,000, times a 10 to get that 0 back that we lost over here, right? So we have 1,000 times 10. That would be the same thing as, oh, wait a minute. I'm sorry. That should be 4 zeros. It should be 10,000. 10,000 times 10. 1, 2, 3, 4 zeros. So 10,000 times 10 is going to be 100,000. That's why it's always good to double check and make sure that you did it right, and that if you multiply these back out, you should still get this number. All right. So now we've broken it down that far. Now we could say, okay, this 10,000, that has an even number of zeros. Let's lose half of them, and we end up with 100. So we know that 100 can come out of the radical. Inside the radical, we still have the 5 times 10, which is going to be 50. And then we can take that and break that down, either doing it this way or remembering that 50 is a product of 25 and 2, and then knowing that root. But if we do it this way, again, we'd have the 5s that'll combine, so we can pull 1 5 out. So we have 100 times the 1 5, which is going to be 500, times the square root of what's left over, which is a 2. All right? So there we go. That would be our solution. If that did not make sense, because I know I kind of did a little bit more in my head on this one, which is what I want you to eventually start doing, go through it, maybe take a couple more steps, and make sure that you can get to this answer. All right? All right, let's try another one. What if we've got, let's try a really big one here. Pull this right out of the book. If we've got the square root of 40 million. All right, the square root of 40 million. And again, if we were to just find the prime factors of this, it'd be a long problem. It's a lot of prime factors. So let's first break this down. Well, actually, again, pause the video, try this one on your own, and then we'll do it together. All right, so let's see how you did. So again, first thing to recognize might be, well, let's just keep doing it the same way that we've been doing it. So if we first try to get this into the form of a 1 with a bunch of zeros, we could say that this would be the equivalent of 4 times 10 million, right? 4 times 10 million. Okay, would give us 40 million. Okay, now this 10 million has 7 zeros, so we need to lose a 0 so that it becomes an even number. So we have 4 times, now since we're losing a 0, we're going to kind of regain that 0 by multiplying it by 10. And then we're losing that 0, and we end up with 1, 2, 3, 4, 5, 6 zeros. So following a 1, 1, 2, 3, 4, 5, 6, right? Which is 1 million. Okay. And again, this should make sense. 4 times 10 is 40. 40 times 1 million is 40 million. You know, when you've done enough of these, you could probably even recognize this at the very beginning. You could probably say, okay, it's an odd number of zeros and it has a 4. So I'm just going to make that an even number of zeros by losing 1, which means I'm going to be in the millions. So I'm going to make it 40 times 1 million within, again, the even number of zeros. And 40 times 1 million is 40 million. So if you can get from here to here, all in your head, that's great. That's a great step. You're just going through it a little bit faster. Okay? We just kind of arrived at the same spot, but just taking a few extra steps here. Okay? So now we have 4 times 10 times 1 million. The million now has an even number of zeros, so we recognize that, and we can say, okay, cross out half of them. All right, cross out 3 of them in this case. We're left with 1,000, so the 1,000 comes out of the radical sign, and we're left with, 4 times 10 on the inside. Now, I might even say, okay, well, I know what the square root of 4 is, too. That's an easy one. Square root of 4 is a 2, so that 2 can come out, and I'd have to multiply it by this 1,000, so I'd end up with 2,000 times the square root of 10. All right? And actually, that's simplified, because if I take the square root of 10, the 10, and find the prime factors, it's just a 2 and a 5. I can't get any pairs out of that. So it's 2,000 times the square root of 10. All right? Excellent. I think that should probably about do us for today. So again, it's nothing too extraordinarily new today. It's simply expanding our knowledge of radicals and how we can manipulate them. So just as a quick recap, what did we learn today? We learned in the beginning here that we can simplify expressions having radicals, and sometimes when we simplify them, we end up with an expression that has similar radicals, and then we can add the expression by adding the coefficients. And then we also learned how to take really large radical numbers, roots, and manipulate them so that we are writing them with an even number of zeros, and then we can erase or drop half of those zeros and pull the remaining number out of the radical, and that saves us a lot of steps, a lot of time when we're solving these radical expressions. All right, very good. So we will stop here, and we will continue tomorrow.